Everyone, welcome back to Code Something. So in the last video, we actually looked into the regression. We did some sort of crude programming to see how the convergence happens. But I thought maybe I can make a detailed video on why we have so many different types of learning algorithms. We have classifications, regressions. We also have reinforcement learning as a new thing. So so for number classification, we have different algorithms. So we need to find which kind of algorithm we need to pick for a given problem. So I thought of like making some videos implementing in Python actually for each algorithm and see the performance so we can compare and also understand for which type of data you can actually use different types of algorithms. So the first thing I'm going to talk about is something called a perceptron, which is a sort of a classifier for a binary classification problem. We can take a look at what a perceptron is on Wikipedia. It says that it's supervised, which means we have a data set having its labels and features, and then it performs a binary classification. Um, so that is, let's say we have some sort of features, right? Um, the popular example we can pick is the iris dataset. You can just Google iris dataset, University of California, Irvine. It'll take you to this page, and you can just click on data folder. You can see that they already have some sort of data sorted out. So the first column represents they actually did some survey and they measured the flowers length and width, um, the sepal length and width, and petal length and width, and then they given the tag which flower it is. That is, let's say they went on search for doing some survey, and then they found out this flower Iris setosa, and then so in that garden they measured these flowers like length, like maybe like a petal length and width, sepal length and width, and then they know which flower it is, right? So then give a tag to it. Okay, which so given this information, and this is actually the flower we have. Similarly, we have like one more flower. Let's say Iris virginica. Um, so we have this flower, and then this is how the flower looks. So it has its own readings. That is, it has its own sepal length and sepal width. So let's say we find a new flower in the garden. So how do we know which flower it is, right? So purely based on measuring the sepal length and width. So how we can classify which flower it is? So since we're talking about binary classification, we're going to consider only two flowers, that is Iris setosa and Iris versicolor. So let's say you find a new flower, you can classify it as either setosa or versicolor. So for mathematical purpose, I'm going to use -1 as a class 1 for Iris setosa and +1 to represent versicolor. That's my second class. And these are my feature vectors. That is sepal length, sepal width, petal length, and petal width. So these things. So now that we have an understanding of what the data looks like, so let's see what a perceptron does. A perceptron is some sort of like a learning logic, which basically makes a prediction, and then it sees that okay, if this prediction is right or wrong. So let's say we give in an input of this features, that is going to be my say x1, x2, x3, and x4. It makes a prediction of either -1 or +1. If it makes a -1, that means we made a right classification. That means okay, we are fine. But if it does make a prediction of +1, which means we are wrong. So we need to go back and change our weights to make a better prediction. So weights are nothing but we multiply the weights for each feature. That is W0, W1 into X1, W2 into X2, W3 into X3, W4 into X4, plus W0. W0 is somewhat of a constant which you're going to use for fine tuning our prediction. So so we initialize all the w's to 0, and then we make a prediction. If you make a right prediction, that's good. If you make a wrong prediction, you're going to go back and change the weights so you can make a right prediction. That's the whole logic of Perceptron. That's what this function says here. So given these features x1, x2 up to xn, we multiply with some weights, and then we're going to make a class prediction yi, and we'll see how it looks. If it's wrong, we're going to go back and change the weights. That's the whole idea of Perceptron. If you look at my previous video in which I made a regression on the gradient descent, we actually took the difference of errors and we took a square of the error, because squaring that actually gives us some sort of parabolic equation which makes us to find the global minima by differentiation, so we can actually make the we can predict the values of weight in a single step. But now we'll not go there. We'll just start with the basic steps, and then we'll improve our coding logic so we can improve our learning rate in the next videos. Okay, let's get started now. Okay, so the thing I'm using something called a pandas. Pandas is a library which you can use the dataset to load from a given URL, and then you can actually process the data for easy handling it. Let me just show how it looks. Import pandas as PD, and then I'm gonna say let me just say it as df. Okay, so df is equals to pd dot read underscore csv from that URL that is here. So if I paste it here and run it, this will have all the data set we need to process it. Now again, in this data set we have three classes, that is Setosa, Wernicke, and Versicolor, but we are working on a binary classification, right? So we need to like remove or chop off few data set we don't need. And also for this video, I'm not going to consider all the features. I'm going to consider only two features, maybe this feature and this feature, so we can see how the implementation works with it. All right, so let me just copy the same line to our code here. And then like while running the code, if you want to see like how the data looks like, you can just run the command df.tl, which basically prints out how the last n number of results look like. So it gives a basic idea of how the data set looks like. Okay, now I need to pick the classes. So y is going to be a variable which holds my classes, that is either Setosa, Wernicke, or different flowers. So to do that, I'm going to just chop that particular columns from the data set. So df.iLocation 0 to 100. I'm going to pick 100 data samples from a training set. I'm going to pick the fourth column, that is my classes dot values. So if I were to run this command, let's see how it looks like. Copy it. Oops, sorry. Okay, now if I print y, you can see like we have two classes here. Now for mathematical purpose, we told we want to encode it as -1 and +1, right? So y is equals to np dot wherever you find y equals to as iris Setosa. So while parsing it, if you find iris Setosa, we're gonna say it as -1. If not, I'm gonna say +1. So if I run this line, oh sorry, import numpy as np. Okay, so if I print this line, we'll see that okay, so for Setosa we have -1, for Versicolor we have +1. All right, so next we're gonna extract all our features. So df.iLocation 0 to 100, that is gonna be my 100 samples. I'm gonna pick 0 and 2, that is my feature 0, and feature 2, that is gonna be this one, and this whole column, 5.1, 4.1, this whole column, and 1.4, 1.4 on this whole column. That's my sepal length and petal length. Okay, so dot values. So that should basically have all my features we need. So if I print it, this is how it looks. All right, so okay, for visualization purpose, I'm gonna do is basically write the plotting code so we can actually graphically visualize how the data is being plotted. So now for that purpose, I've actually already checked in the code on GitHub, so you can probably see it there. I'm just gonna copy paste it in with respect to time, so I can actually make it much quicker. So paste all it. So this is basically gonna take all my features and plot it on my y and x axis, and each class will be plotted as a graph in value on this sheet. The red color with the marker as O will be my setosa, and blue color with my x marker will be versicolor on the graph sheet. So let's just run this thing and see how it looks. Oh, sorry, I think I. Okay, there we go. Okay, so this is how the data set looks like. So we have all the sepal length on the y-axis and the petal length on the sepal length on the x-axis and then petal length on the y-axis, and then each scatter plot shows which is setosa and which is versicolor. So what we're trying to find here is basically some sort of line which bifurcates the data points. So whenever we find a new data points, we just plot it on the graph and we can see which side it belongs to. So if it belongs to this side of the line, we can say that okay, it belongs to versicolor, or if it belongs to this side of the decision line, we're going to say it as belongs to setosa. That's what we're trying to find actually. Okay, so I'm going to just comment this whole plotting thing, and we'll go ahead and implement the learning function. Now for implementing the Perceptron, so we're gonna create a class called Perceptron, and then we'll go from there. Okay, so our class Perceptron will take Perceptron. Okay, it's gonna take an object which is gonna be my like information on like the features and classes and stuff. So def init self. Okay, so ETA is gonna be something like it's actually learning rate, that is how quick you want the algorithm to learn the weights W. So again, like if you have a lot of very small ETA, it's going to take a lot of time to converge because it takes very small steps. And if you have long one, it's going to take quick steps, but it's not going to make a very good convergence. So it's going to learn some bad weights. So we need to actually optimize this. We need to make this adaptive learning rate. We will look into future videos how we can actually make this ETA variable so we can actually learn as we go through the process. So but now we'll just fix it to 0.01 and then maybe iterations to 10. That is, we'll try to stop our logic after 10 iterations. Okay, self.eta will be my ETA, and then self.iteration will be iteration. So that's done. Okay, so when I create three functions, one function will be called fit, in which we will try to learn based on our prediction. We'll try to learn what was the error, and we'll update our weights. And then we'll have one more function called as predict, in which basically we actually make the prediction of which class it belongs to, it's going to take my features as an input, and then we have one more function called net underscore input, which again takes the features to make prediction. So okay, let's just see what actually, let's implement this particular component, that is the multiplication of weights in this thing. So when I use the linear algebra concept of multiplication of two matrices to do this job in a single shot, so we can just return dot product np dot of my features x and self dot weight. I've not defined the weight yet. I'll come back to it later. I'm just gonna start with from here and then go from there. Self dot weight. So I'm gonna take a dot product of these two and then add a constant self dot w underscore 0. So what this line is basically doing is something like this. It's going to take all features, something like let's take an example, maybe like 5.1 and 0.4. So 5.1 and 1.4, and then it's going to multiply with some weight w1 w2. So that's going to be something like 5.1 into w1 plus 1.4 w2, the whole thing plus w naught. That's what it's basically doing for a single sample. Now again, this is actually for a single sample, right? But if you have like say 100 samples, you can make a single dot product on matrices to make multiplication much quicker. All right, let's go to the fit part. So the first thing I'm going to do is basically take a variable called weights, in which we actually use it here, and initialize it to zeros. So np dot zeros. So I'm going to add one more dimension for the constant x plus shape. This gives me the size of the actual feature vectors. Okay, now that we have that, I'm going to keep track of errors when I get over each iteration. So my errors would be equals to initialize null for null array, and then we can actually compute for the next steps. So xi will be my individual feature, and the target will be actual class which it belongs to. So in zip of x comma y. So this loop, xi will be holding my feature vector for a given sample. That is, in the case of in this case it would be 5.1 1.4 will be held in xi, and then y will be -1 for setosa. That's how the loop runs. So we're going to compute the error for wrong classification. So to do that, I'm going to take and multiply my learning rate ETA into target, that is the actual class from our data set, from our training data set, minus our predicted class xi. You just pass the predict to this input xi and then make some prediction, and then give the value to it, and then we'll check what's the actual class it belongs to minus what the class which we predict. That's the error, and that's what we need to update for our weights. So once we have this thing, we need to say self dot w score 1 dot this thing. So basically we can update all the weights, plus equals to update the error into xi, and then we'll update the constant as well. There's w underscore 0 plus equals to update. So when we run this loop, basically we're going to take each sample, we'll see what the predictor class is, and then compute the error, and then we update our weights over the loop. And then we'll keep track of errors for each iteration we make. So plus equals to int of update not equals to 0.0. And then finally we'll just append to our errors, so we can keep track of all the errors we make. Dot append errors. And now for prediction, we'll just return np dot where self dot net underscore input. That is, we basically run this function, we find the actual class it belongs. There is we make some prediction on which class it belongs to, and then if the prediction is, that is the error we're going to compute, actually it's going to be greater than the threshold of 0.01, we're going to say it as positive 1. If not, it's negative 1. And this prediction is being used here for updating our errors. And that's the implementation of Perceptron. Okay, I think it should be complete now. So let's go ahead and run this thing and see how it looks. So okay, here we go. So we created a class called Perceptron, so I'm just going to call it Perceptron, Perceptron, and then our learning rate, let's say 0.1, and then iteration equals to 10. Let's call it a pp, and that's a Perceptron input. So once we have this information, we can just try to fit it, but in this function fit by passing the features and classes y. So once it has run everything, we can actually see what the weights it has learned to make a good I think I missed something here. Let me just see. Oh yeah, I think I missed returning the actual values. So this function should return, okay, the learned variables. Let's see, software variable letters. Okay. Oh, I think I missed something as well. Okay, so this is what happened. So we actually took only one sample here. We didn't run over entire data set. So that's something I have to be more careful about. So for this in range self dot and underscore iteration. So we're gonna run this thing 10 times to find this error. So I'm going to initialize my errors to 0 in this case. Okay, then this should be tab, 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 and then tab, tab. Okay, so now we're going to run this thing 10 times, and then we'll update our errors or iteration, and then we'll return the value. So this should actually fix it. So before reading, let's just print out the self.w so we can actually see what the learned weights are. All right, let's run this thing and see. Okay, there's something. What happened here? Okay, np.0s1 plus x dot shape. Oh, I'm sorry. My bad. This is actually a tuple. Mm, 26. Okay, np.where this thing self.net underscore input. Oh, we didn't pass the features. Line 20. Oh, so many errors. I didn't. Oh, this has to be errors. Let's see, what is this? Oh, self.w. Oh, so many syntax errors. I'm sorry, guys, but oh, there we go. So for this data set, the Perceptron looped over 10 times, computing the errors, and then updating the errors, and then finally found out that okay, this vector bifurcates the data points. So if I were to find a new sample, I'll just plot in the graph and see which side it belongs to over this line, and we can classify it to that particular class. Now, to visualize this, actually, I checked in the code on GitHub. You can probably check it out from there. I'm just going to copy the function and paste it here so we can visualize it and see how it looks. So this function will basically plot the line and the classes on the data set so we can see how it looks. Okay. And then the plot samples. All right, let's run this thing and see how it looks. Okay, so we can see here the algorithm has learned that this vector, that is this vector, bifurcates the data points like this. So we can see that it has learned to bifurcate the data points. Now let's say how much time it took to converge. Well, we actually run this loop 10 times, right? It's not an ideal thing. We're supposed to run some sort of regression or gradient descent so it can converge by itself. So you can make much more accurate prediction. That is, we want the line to be more accurate so it can be applicable to more data points. So in the future videos, we'll try to learn how we can extend this code to implement gradient descent so we can actually make much more better classification. And also we'll try to learn, like we have something called a regression term, which is basically the constant I was talking about. We need to modify the regression term so we can actually fine tune. So we don't want to, like, let's say this data point is fine. Let's say we have like much more complex data points. So we don't want to put up like, this is a linear classifier because it has a single line. Let's say we go for like much more, maybe higher order, like maybe quadratic function, which basically maybe like a curve. So in that case, we don't want to overfit or underfit it, right? So we're going to use regression term to make sure we don't overfit the data points. So I think in the future videos, we'll try to cover much more different types of classification. This is actually a simple adaptive linear classifier. We also have something called the logistic regression classifiers, and then we can see how we can actually use regression is actually to make a prediction of a numerical value. This actually classifier basically classifies to positive, negative, or A or B or C. So we'll try to look difference between what regression is and what classifier is in our future videos. All right, thanks for watching.